So now to expand to our polynomial functions, which from our notation can look like a big jump here. But we're going to want to keep those power functions in mind with their kind of general shape of their graphs, that long-run behavior that they hold in their general form. That's in here, but what we can see is when we expand to a polynomial. So at the front here, here's our power function that we've been working with. What a polynomial function does is that then we can add on terms of a similar setup where we have numerical coefficient, x with some exponent, and numerical coefficient, x, and an exponent of 1. And we could even have that case where it's just a numerical coefficient. This would technically have x to the power of 0 there, and there's our x to the power of 1, but we don't need to write those because it's redundant. So general form of a polynomial is that we can have this term, and this would have the highest, it would be called the degree, coming from that exponent right there. So the power functions that we've been working with is going to relate to this kind of highest degree term. But then what we could see is adding on is every degree below that. So for example, let's say I had a function, some polynomial function that was negative 3x to the 7th plus 2x to the 4th minus 3.1 x squared plus 2. That right there is a polynomial function. How I know that is that I have these numerical coefficients that are all real numbers. I have my value of x, and these values of x have exponents that are non-negative integers. So again, I can have an exponent of 0 like we saw at the end here, that's fine, but we can't see negative exponents, we can't see rational exponents, so I don't want to see any fractions for exponents there. So with that, this would be my leading term. So let's see here, where a with the subscript, those are just our numerical coefficients that are real numbers, and n is a non-negative integer. The leading term is coming from, and that's going to relate to our power functions as we look at it. So with my polynomial up above here, that negative 3x to the 7th, because it has the largest exponent, that makes this the leading term. So the leading term has the highest degree or highest exponent. Now what we're going to see when we start graphing our polynomial functions is this leading term is going to determine the long-run behavior of our graph. So we'll talk about that more when we get to graphing polynomial functions, but this leading term is going to be very important to identify so that we can get a general form for our graph, and especially what's happening out at infinity. The degree of the polynomial is that exponent n. So degree relates to exponent. All right, so let's practice with some of these terms that we're talking about and relating them to our polynomials. So right here, we have a polynomial. In fact, it's quadratic. It has a special name to it, but quadratic functions are also polynomials. If it helps, you can write these in standard form. So standard form is where the degrees would decrease as you read left to right. So if you wanted to, we could take that 5.6 x squared and have that out front, and then the minus 3.5x, and then the plus 1.4. Sometimes having in this form could be helpful, and then you have your leading term actually leading and not mixed in. So the polynomial doesn't have to be in order, but you can always put it into order. That helps. So the leading term is that highest degree term, so that 5.6 x squared. What is the degree of this polynomial? So the degree is coming from the exponent, so it's that value of n. In this case, it's that exponent of 2. What are the terms in this polynomial? So as a refresher, term in mathematics, these are what's separated by addition, subtraction. So this is the case where we have 1, 2, 3 terms. So the terms we have the 5.6x squared. That's one term. Another term with subtraction between it, we detach the negative, so that'd be a negative 3.5x is another term. And our last term would be this positive 1.4. We don't need to put the plus symbol, just write it as positive 1.4. So those are our three terms. What are the degrees of each of the terms in this polynomial? So the degree of this first term would be that exponent of 2. The degree of the second term would be an exponent of 1. That's actually on x there. And this last term, which we call the constant term, would have a degree of 0 because of that hidden x to the 0 power that's technically multiplying with it that we just don't write out. How many terms does this polynomial have? 3 terms, because we have 1, 2, 3. All right, last piece here, kind of working with the same terminology, but with a bigger polynomial. So we have this great big polynomial. Again, to identify that it is a polynomial, I can see these real number numerical coefficients in there, so that's all good. My variable x, if I look at the exponents, so 7, 5, 4, 3, 1, 0, that's perfect because they're all positive, they're non-negative numbers. And that non-negative, it's a little different from saying positive integers because we want to include 0 in there. Having an exponent 0 is fine. So that's why they use that wording of non-negative so that we have 0 and higher. So listing our terms. So we're looking for this separation at the addition subtraction symbols. So we're going to have these different terms here. So we're going to have negative 3x to the 7th, positive 4x to the 5th, negative x to the 4th, positive 1/2 x cubed, positive 1x, and the negative 9. The coefficient of these, so this is the numerical part that's multiplying out front. So our coefficient would be negative 3, a positive 4. This would have a negative 1 coefficient, a positive 1/2 coefficient, a coefficient of 1, and this would have a coefficient of negative 9. The degree is coming from the exponent, so this would have an exponent of 7, 5, 4, 3, 1, and then this last one would be 0. So there's our polynomial function and some terminology to go with it.